This video deals with a couple of Comfort Total mini split heat pumps that I've installed in my home here. It's not a how to install type of video, but it deals with the expected heat pump output and measurement of that output heat. I've also compared it to a competitor unit to see how this unit competes with another unit. This is the Comfort mini split system Comfort Total unit. As you see here, this unit is the indoor unit in the master bedroom, and right now you see it flashing 72, which means the thermostat is set at 72, and when the unit begins to run, why the temperature, the number display will go solid. The unit, what is a little different about this unit is you see the power cord going down the wall behind the mirror, and since this is a 120 volt unit, it is just plugged into an extension cord into the receptacle circuit. The unit maxes out at about 11 amp draw and really takes pretty much the capacity of this circuit, but again, this circuit just serves the receptacles in our bedroom, and at 11 amps it still leaves enough capacity to run, a few miscellaneous things in the bedroom. Now let's go outside and we'll take a look at the outdoor portion. I don't believe I mentioned it previously, but this is a little 1-ton 12,000 BTU mini split heat pump, and as you can see, I've just covered the line set with a piece of guttering material that was split and moved over the line set to give some protection. Again, I'm not terribly proud of the carpentry work here, but this was on a location where the ground was sloping, and I really didn't want to bring in fill material in order to set a concrete pad, and I had a bunch of leftover salvaged treated lumber, so at least its temporary equipment pad is fabricated from salvaged lumber. Now you see the second unit installed in this house. Its appearance is identical, except in this particular case the unit is in operation, so the digital display is constant, it's not blinking. This is a 18,000 BTU unit located in what we call our great room, or our recreation room, down on the lower floor of the house. Now I'll take you outside and take a look at this unit's outdoor portion. Okay, now we're outside the house looking at the outdoor unit for the 1.5 ton for 18,000 BTU unit, and as you can see, it's located, has been installed on a concrete stoop, and it's protected by a balcony, a wood balcony up above it. Now this unit does require 240 volt power, so in this particular case you can see a gray conduit coming in here. I brought in a 240 volt circuit and I installed a disconnect for it here. This unit was also equipped with a 240 volt plug and cord assembly, but I just cut the plug off and attached it directly to the disconnect switch, and this becomes the disconnect for the unit. In this particular case, the line set is covered with a box that I made out of from really scrap material. This is 1 inch thick decking material. It's a synthetic material. Should have a long life, and I just had some scrap material that I used to make a cover for it. The unit is, as you could easily tell here, is located on a concrete slab, and you may notice that the dampness right at the bottom. One of the things when I set it on this slab I really didn't think about was, of course, the condensate that the outdoor unit releases when it's in the heating mode. And today it is on, and it's in the heating mode. And so what I did was to apply a bit of, well, it's actually body filler, to create a dam, and then drilled a hole through the slab to corral the condensate. Obviously, what I hadn't thought about when I put this on the step was that, or on the stoop, was that the condensate, when it's cold, is going to run across here and make a little mini glacier, which is not too neat. So hopefully this is going to corral my condensate and just drain it into the ground underneath the slab. The slab's probably about 6 inches thick, so it's pretty substantial. Well, now let's kind of take a look at the interior of one of these condensing or outdoor units. Here you see the condensate line. This is from the indoor unit coming down. Again, there was a small hole drilled in the slab, and it's allowed just to, any condensate is just allowed to run down that hole to get rid of the condensate. Now this unit is operating. I'm going to at least lift the top off here, hopefully without catastrophe. And you can see the outdoor, I guess you should call this, the outdoor unit here is pretty simple. You see here just the capacitor for the compressor. Here is the switchover valve to change from heating to cooling. Right here, trying not to touch anything live, is the capacitor, run capacitor for the fan motor. And here is the fan motor, of course. You notice there, it's a pretty quiet unit. Because this is a constant speed compressor, no circuit boards required for the outdoor unit. So this is, a relatively low cost unit, and very basic in its design. Once you get this unit up and running, knowing that it's perhaps one of the cheaper models manufactured, the question is just how much output are we getting out of this unit? And this follows a typical design for this unit, in which air is returned through a grill located in the top, and the coil surrounds the blower unit, and then the discharge air, of course, comes out this lower opening down here. Well, the technique for measuring the output heat of the unit turns out not to be terribly complicated. Basically, if you know the temperature of the air going in at the top and the temperature of the air coming out at the bottom, if you take the difference between those two temperatures, multiply it times the quantity of air flowing through the unit, times 1.8, this equation gives you the output of the unit in BTUs per hour. Of course, what is simple mathematically and simple in theory is sometimes a little bit difficult. I tried first to use an anemometer here and basically measure the airflow along the front of the unit with this small propeller type anemometer. And the results I got were not too dependable. It seems as though when I tried to repeat it, there was a lot of turbulence in the air coming out of the unit. So I then tried putting a cardboard rectangle discharge off the end of the unit coming toward me, and it was, I don't know, maybe 30 inches long. It straightened the air out, but it seemed to restrict the flow, and I still did not obtain the airflow that I expected. Now, typically, the rule of thumb is about 400 CFM, cubic feet per minute, per ton of capacity. Since this is 1.5 tons, maybe 600 CFM might be a reasonable number, give or take a little bit, depending on the design. And I wasn't getting anywhere near that quantity of air. So my next approach was to fabricate a more rigid box. This is just made of insulated foam, 3/4 inch insulated foam. It has the advantage of being relatively rigid, yet very lightweight. And it's about, opening is about 4 inches by 27.5 inches wide. However, the intake, it runs the full width of the unit. It's about 6 inches high. And also there's a section here that transitions, making this discharge area slightly smaller. It turns out this right-hand side of the unit is pretty much dead. In fact, the discharge opening even is not as wide as this louver. It's about the end of my pointer is the where the air actually comes out from here to this side. So I took this box, put it up against the unit, then used a duct tape to hold the unit up here, and this is light enough that the duct tape could hold it, and then went around the perimeter. Excuse me, I don't have that on very straight. Then went around the perimeter with duct tape to seal around it to reduce the leakage. Then I took once I had this in place, I took my anemometer, it measured at 10 locations, and I found that the airflow was much less turbulent. This length of box allowed the air to straighten out, and it was not completely uniform all the way across, but at least I didn't have the turbulence. You know, in some cases I almost had the air flowing in a reverse direction right up against the unit, and this really straightened it out and made it easier to measure. So again, what I have done is I had a thermometer at the top of the unit, thermometer on the discharge, measured the difference in the temperature. I had 10 readings that I made across the face of this, generally lower part, lower part, lower part, upper part, upper part, upper part, and then we're right down the center. Averaged those up and took those readings. The average of those readings was taken, and I calculated based on the volume of the area of the discharge opening, and it came up with 457 cubic feet per minute. So this is still a bit below, you know, maybe the expected airflow, and I did go on to Comfort Total website, and they had this data sheet which I have in my hand here, and looked down through the specifications. This was just printed off of their website, and it said that the airflow for their 1.5 ton unit was 850 cubic meters per hour. Well, when I converted that to cubic feet per minute, I came up with 500. So they're saying in their literature 500 cubic feet per minute is being the airflow for this unit. Oh, incidentally, that's with this unit set at full speed. You can set the speed of the unit. It has 3 different output settings, and I would just set the speed of the fan at maximum to get maximum airflow, assuming maximum airflow is going to give me maximum heat output. And so 457 feet per cubic feet per minute is about, what is that, 92% of what the literature said. So I felt fairly comfortable that I had an airflow at maximum fan speed. So using that, like I said, the change in temperature from inlet to outlet, multiply that times 1.08, and that gave me BTUs per hour. So when you see numbers later, this was how it was obtained. It's not extremely scientific, it's not lab quality. The temperature was only measured in one place, approximately right here. I had a digital thermometer that was taped right across this area, and a second thermometer located at the air intake. And then also had another digital thermometer located outside at the air intake to the outdoor unit. So that was, when I refer to outdoor temperature, that is the temperature that I was using in my calculations and all the data that you see. Okay, now I'll hold up. This is, I hope I can hold this steady enough for you to at least see approximately. This was just my rough data sheet. Basically, on the left-hand side is the outdoor temperature. Then I recorded the inlet and the outlet temperature, subtracted the two, and there's a column there that has a delta T, that is the temperature difference. Then there is a column where I calculated the number of BTUs per hour, and I also recorded the input power, which allowed me to calculate the coefficient of performance, which my definition of coefficient of performance is that it is the number of watts of output versus the number of watts of input power at any given period of time. Okay, so now how did I determine what the input power was? Let's go look at that. Now we're in my garage, and you see my electrical service panel is to the left, and to the right of it is a small panel with 5 meters in it. Now, pardon while I wobble around here, but what happens is that inside each meter has a current transformer, 2000 to 1 current transformer. It's a donut shaped thing, so one of the conductors of the circuit goes through that donut, and it's hanging inside the power panel, and then it sends a very small current to the meter, and this is interpreted then in terms of getting kilowatt hours and kilowatts of power and so forth, consumed by the device. So each meter is capable of up to about 100 amps. So 2000 to 1, that means that the current going to the little meter divided by 2000, that'd be about 50 milliamps. So the whole thing is wired with very light duty 16 gauge wire, which travels through this flexible conduit down behind this wood panel and up into the bottom of our panel where the current transformers reside. So let me step a bit closer and try to show you a bit more detail. The top two meters, one of them is labeled furnace blower and 10 kW resistance heat, and the one right beside it is 5 kW resistance heat. Well, this is on the main air handler for the 5-ton central heat pump system that serves the house, and again, the meter, the top left meter is recording the power that's consumed by the blower motor, and when it's needed, while the resistance heat is turned on, and there's a 10 kW resistance heat available. And again, to the right, the 5 kW resistance heat is just supplemental heat. So when the unit calls for resistance heat, we've got nearly 15 kW resistance heat that can come on. Now, this only comes on if the refrigerant part of it that doesn't carry the heating load, or it's defrosting at the time. And then to the left again, the 5-ton outdoor unit is the outdoor unit that is the 5-ton heat pump. This is the refrigeration part of it. That's the meter which records the amount of power being consumed by the 5-ton unit. And then the basement great room, 1.5 ton. This is the unit that we were just looking at a few minutes ago. And right now, you can see that it is online. The basement heat pump unit is online. It's drawing 1.58 kW power, 6.8 amps. The voltage going in is 244 volts. The power factor is 0.94. And there's 418 kilowatt hours accumulated power consumption since this meter's been started up. And then the 60 at the bottom right just means that it's 60 cycle power. Just below it is another meter, and you notice this one reads 123 volts. This is goes to the circuit which feeds the small 1-ton unit that's located in our bedroom. And right now it's only, well, it's less than, a little over, about 24 watts. And so what I'm seeing there is probably not the heat pump, but a little bit of power going to the heat pump, but mostly that 24 watts is made up of, a clock radio, a couple of radios, the charging station for the telephone and so forth. So anyway, this is where I get my information for how much power my heat pump is using. Okay, now having calculated this data, how would we use it? Or I said calculate, I actually recorded this data. Well, if we take the relationship 1.08 times the CFM, cubic feet per minute, that is air that's flowing through the air handler, the indoor air handler, and we multiply that times delta T, and delta T stands for the difference in the temperature between the inlet and outlet air flowing through the unit. We come up with BTUs per hour. Okay, so that gives us that gives us our output of the unit. Now, if we know the input wattage, I'll just say, well, we'll call it kW, I for N, which we recorded from our meter out in the garage. And we know the BTUs per hour. If we took the BTUs per hour and we divide that by 3,412, I'm sorry, that is a 3, folks. There are 3,412 BTUs per kilowatt. That's BTUs per kilowatt. And we take that number and we divide it by the kilowatts of input. So now we got kilowatts over kilowatts, and that's my definition of coefficient of performance. So that's usually going to be a number of 3 would be nice, but certainly in the 2 to 3 range, and it does vary depending on how the unit's doing. I took the information from my handwritten notes and I put that information into a spreadsheet and asked the spreadsheet then to plot the data. This would be my data set that I was using, and this would be a plot of the output in thousands of BTUs per hour versus temperature, 0 degrees Fahrenheit here, 50 degrees here. So you notice a generally downturning curve, which is very characteristic of any heat pump. It's the sort of thing that the heat pump salesman doesn't like to talk about, and that being that the colder the outdoor air is, less heat you get out of it, the less heat you get out of your heat pump. So, you know, if your building is requiring more and more heat because the temperature outside is getting colder and colder, that you actually have less and less heat from your heat pump to take care of it. So it gets to be a balancing point of trying to get the amount of heat in to the building to match the amount of heat going out through the walls and infiltration and so forth. You notice that peculiar little hitch right here. When I looked at that, I thought, well, what happened there? And I looked at my notes on my handwritten notes when I took this data, and the one to the left here is at 18 degrees, and the one to the right down here at the bottom is at 19 degrees. And the question is, well, why do I have a higher output at 18 degrees than I do at 19 degrees? And I think the reason is that I made a note that when I took the reading in the 19 degree time, there was a considerable amount of ice on the outdoor coils of the outdoor unit, and the next time at 18 degrees, which was probably a different day, I'm sure it was a different day actually, this coil was nice and clean. So that divot is probably the result of lost capacity due to ice on the coil. So some of these little divots, you know, it's not a nice straight line. Some of it may be recording error, some of it may actually be because the outdoor coil had more ice than at other times. Also up here, you notice that this is the 20,000 BTU, and this unit is a 1.5 ton or 18,000. I'm actually above the capacity here at about 57 degrees. And I noticed that when I looked at that data, I had two readings taken at this 57-degree period, just minutes separating the two. And in reality, what apparently is happening here is that the output would go up to, let's say, this was at, let me look at my notes here, 21,223, and then a few minutes later it would fall down to about 18,200 to 18,300, just below this line, within minutes of one another. And then I realized what's happening is that this unit shuts off the outside fan to control the loading on the compressor, and actually the loading gets higher and higher as the outdoor temperature goes to the right here. So to unload in the heating mode, to unload the compressor, the outdoor fan is cycled on and off by the controller unit, and apparently it's sensing, I suspect it's sensing the temperature of the liquid line coming back, and when it gets too high, it shuts the fan off, the airflow drops, the output drops back down, and then it'll sit there and cycle back and forth, back and forth. And I've noticed that seems to happen, well, usually when it's above around 50 degrees outside. When it's lower than this, the outdoor fan seems to run pretty much steady at all times. So the short answer here is, yeah, this unit does produce its rated output. Actually, when the temperature is warm enough, it goes a bit above its rated output for a period of time, but it does drop off as the outdoor temperature drops off in a typical fashion. I wanted to compare the output of this CONFORTOTAL unit with a competitor of some sort, and I had been online and I came across a manufacturer, that model is called Blue Ridge, and they have a very nice website. And the nice thing about their website is that their units have published tables. I'll just show this very quickly. These are tables that give output of their units at both for cooling and heating at various temperatures. And so I went with their low-end unit, which is, I think, a step above the model I purchased, the CONFORTOTAL, because it does have the variable speed drive, and the CONFORTOTAL is just a constant speed compressor. So this has the higher, more complicated electronics in it, and I wanted to kind of compare to see how this CONFORTOTAL unit did as far as output as compared to the Blue Ridge unit. And the blue dots down to 18 degrees here, from here to here, this is the data again from my CONFORTOTAL, and the red dots go all the way down to about 5 degrees here, and they are the outputs at various temperatures for the Blue Ridge unit. And as you can see, I was favorably impressed that the CONFORTOTAL's outputs were just right in the plot lines, in some cases above. Of course, this could be error, who knows, but just right in the plot lines with the Blue Ridge unit, and it's, you know, definitely a more expensive unit. I think that this I thought, well, perhaps Okay, so they do put out similar heat outputs. What about the power that they consume while they're doing that? Now I've changed plots. The same two units, CONFORTOTAL and the Blue Ridge unit, the same model. But now I've got the amount of input power going to the unit in kilowatts along this border, this axis, and along the bottom axis is the again the temperature in degrees Fahrenheit. And again, the CONFORTOTAL unit held its own. It's right in amongst, at least over the range. Again, of course, I only had data down to 18 degrees, but again, the CONFORTOTAL is staying right in the same range as the Blue Ridge unit. So I found this impressive for since again the Blue Ridge unit has the variable speed drive and is significantly more expensive. I may find this of some interest. The Blue Ridge people have a number of units, perhaps at least 4 levels, maybe more than that, of capacities and efficiency ratings. And this particular one, the 1824, is again a 1.5-ton unit. But this is the plot of the output in BTUs versus temperature again, and they go down to minus 20 degrees here. But what I find interesting, this unit is plotted all the way up to, this is 80 degrees here approximately, and you can see it's sliding down below the 20,000 BTU. There's about 18,000, 1.5 tons. But as it drops back in temperature, it climbs and climbs and climbs, gets up to around 24,000, and before it begins to fall off in the characteristic downward trend. And one would suspect that this part of the curve, they're using the variable speed drive to squeeze the output down to get it more nearly the 18,000 BTU capacity. And as it begins to pick up load, I assume they're of the opinion that it's going to pick up some heating load here around 40-50 degrees. Probably at this point, they're allowing the compressor to run more or less full speed and all the way out. Well, what is kind of interesting about this, they're calling this an 18,000 BTU machine, but in reality, it's more like a 2-ton machine, 24,000 BTU unit, masquerading as a 18,000 BTU unit. So, and the thing to keep in the back of your mind is this unit versus the other unit that I was originally comparing the CONFORTOTAL to. The cost between these two is nearly double. So this unit is what you're paying for is this extra capacity down toward the low temperature range, and it's almost as though they're using the guts for a 2-ton unit in order to extend this and get a higher output at the lower temperature range. Again, if I put this into our view, the red dots again being the other unit, they don't show anything below about 5 or 6 degrees down here, and it has the same characteristic as the CONFORTOTAL unit, if you were to draw a line between all the red dots, that is. But this unit doesn't start that downhill fall due to outdoor temperature until it gets down around, well, what is it, 19 or 20 degrees. So really anything from about 19 degrees up through 75 or 80 in here. This whole area, it's getting in excess of 18,000 BTUs of heating capacity, but you are dearly paying for that with a unit that costs about twice what the other unit costs. Just a couple of thoughts about cost. I guess we'd call this the top of the line Blue Ridge unit with the extended capacity down here in the low temperature ranges is listed on their website as $2,159. Now again, this Blue Ridge, the low end of the Blue Ridge, which is the one I plotted here in the red letters, and they show heat output down to about 5 degrees here, which is running around 8,000–9,000 BTUs, and they're showing that unit priced at $1,089. And then the Comfort Total was shipped to my house at $749. Now, the prices that I've shown here, in the base price for the Blue Ridge unit is just for the indoor and outdoor unit. Then you have to add a line set, a drain line, and a control cable. And so I have added those cost figures here to these two Blue Ridge figures. So if you just go on their line site and website and see that they have a lower price than that, and don't forget you've got to add that information, that equipment, excuse me, those accessories. But in the case of the Comfort Total, those accessories are included in the package cost. I'm not sure, if this is around, let's say 9,000 BTUs, Blue Ridge, would you be better off buying two of these? You still might have slightly less invested in it than if you bought their top of the line unit, and you'd have additional cooling capacity in the summer with two units. Run one when you need it, and then when the extreme weather, run two, or consider two Comfort Total. I expect, but I don't know, but I would expect that my Comfort Total will slide down just like the Blue Ridge unit did, and probably at 5 degrees it will be around 8,000 or 9,000 BTUs, and it'll continue on down here. So far as I know, there's no reason that I can't operate it at sub-zero weather conditions. There's nothing indicated in the owner's manuals that say that I can't. It's just that the output of the unit will probably continue to go down just about along this shape of this curve. I am a bit disappointed in the variable speed compressor. I expected to see energy savings, which at least in my testing didn't show out. It seems as though my Comfort Total unit with the constant speed compressor did practically as well as the variable speed. But I don't want to claim that the Comfort Total is an equal to the variable speed compressor unit that is sold by Blue Ridge. All I can say is my numbers seem to support the Comfort Total as being a pretty good competitor and at a much lower cost. I think I say in summary that again, I don't know, I need to point out that I really don't know how this unit's going to act down as the temperature gets colder and colder here. I've implied that I think it'll probably follow this curve on down like so, but I don't know that because I ran out of cold weather conditions by the time I got my unit up and running, and probably won't know until next year when I can get some colder temperatures to test it. But so far I've been very favorably impressed with what it's done. But I don't want to oversell it because I don't know what it will really do. The other unknowns is, of course, this is so far the information that I've collected has been only concerning the heating output of the unit, from 18 degrees and higher. So I have a limited amount of information. It's just that what I have looks to me to be really good. And I haven't put this unit through a cooling cycle, so I need to find out, how's it going to perform during cooling mode. I think it's obvious as I look at just the cut sheets on the units that the Blue Ridge, to be fair to it, looks like the casing on the outdoor unit is perhaps a heavier quality. The CONFORTOTAL uses plastic grills, whereas it appears that the Blue Ridge unit may have a welded steel grill over the discharge. I also don't know that on the units that run for extended use in cold weather conditions, sub-zero weather, they often have a resistance heater in the bottom of the unit that comes on during the defrost cycle to keep the condensate that's draining down from freezing before it has a chance to run out of the casing. So I don't know that I know for a fact that the CONFORTOTAL unit does not have any kind of auxiliary heating equipment in it. When I look back on the video clips, I noticed that I hadn't said anything about the warranty or guarantees associated with the CONFORTOTAL or the Blue Ridge heat pumps. The CONFORTOTAL has a warranty of 5 years on the compressor and 1 year on the remaining parts. However, the warranty says that the warranty does not apply if the units are unless they are installed by a licensed HVAC contractor. That doesn't warm the heart of this particular do-it-yourself sort of guy. Now, the standard warranty for the Blue Ridge unit is 5 years on parts and 7 years on the compressor. And though there is some wording about if the unit is damage that results from the unit not being installed properly and making the warranty invalid, it has none of the harsh statements about the necessity of having a HVAC professional contractor install the unit. Well, thanks for watching. I hope that you found some of this of interest and perhaps useful. Goodbye. Just one last thing. I have included some links to websites where you can locate some of the equipment that was seen in this video. And also I have included a copy of my data set, my rough data set, so that if you should want to check into it further or compare my data against your own or some other equipment, it's available in the notes. And again, thank you.